Um, I want to talk to you guys about some important notation um, for derivatives. And so we have different ways of writing derivatives. So for example, if I write, so let's say you have a function I'm going to call it f of x. Then the derivative is going to equal to f prime of x. Okay, so that's the first way that but then we also have another way of writing it, and that's called Leibniz notation. And Leibniz notation is very useful in a lot of different ways. So let me just kind of go through that real quick. We have, so instead of writing f of x as f of x, I'm going to also write it as y. And so so here you plug in an x value and you get a y value. It doesn't have to be y, but that's just what it is for this example. Now the derivative, another way of writing the derivative is, this is Leibniz notation, dy over dx. Now what this means is, the way to read this is the derivative of y, and then this tells you with respect to what quantity you're getting the derivative of. So that's one of the advantages. So here what it's saying is that x is the independent variable, and so this this function, the independent variable, is x, and then we'll have different situations later. Another thing is that even though the derivative isn't actually a fraction, remember it's a limit of ratios. So here, for example, if you look at this as the slope of the tangent line, this is the rise of the tangent line, and this is the run. And so if you remember when we were explaining it earlier, both of these are going towards 0, and so this notation kind of breaks it up into its pieces, and that's going to be useful later. Okay, now another way of using it is as an operator. So let me erase this guy real quick. So okay, so for example, we already have several operators. We know the plus sign is an operator, minus sign, for example, times, divide. These are all operators because, for example, if you have 4 and then plus 2, this operator right here, that's telling you, hey buddy, add these two numbers for me right now. And you would say, okay, well that equals to 6. In the same way, you have the derivative operator. Now, so the derivative operator looks like this. It looks like d over dx, and then you have a parentheses. And so here, for example, we've got x squared, let's say. And so what this tells you, this is asking you to do something. This is saying, hey, mister, why don't you get to work and find the derivative of x squared. So that's why it's an operator, because it's telling you to do something. And so then you would find the derivative of x squared, which ends up being 2x. Okay, so we're going to go through some of the basic rules. Now, we're not going to prove any of them. We're just going to go over them, and the proofs I'm going to do in a separate video. So the first type of function that I want to look at is constant functions. If I take a look at a function, a constant function, for example, f of x equals to 4, if you try to graph this guy, you should be able to find the derivative relatively easily. So f of x equals to 4 is a horizontal line. And so remember, the derivative of this function is the slope of the tangent line. Well, the slope is equal to 0 because it's a horizontal line. So that means that the derivative of this function is equal to 0. And you can generalize this for any constant function. Then that let me put it over here, the derivative of any constant c is going to equal to 0. Okay, now the next rule, and very useful rule, is let me erase this, or I'll just go down a little bit. It's called the power rule. Now the power rule says the derivative of x raised to any power is equal to n times x raised to the n minus 1. Okay, now another way of thinking about this guy is this is the hammer rule. The hammer rule, because if you take a hammer and so imagine that you hit this guy with a hammer, bam. This is a sledgehammer, in case you've noticed. This guy comes down in front, and then it's kind of like this guy loses a marble. So that's how you find the derivative of x raised to any power. So let's do an example. Let's say you want to find, you've got a function. Let's say you've got let's say you've got x to the 4th. You want to find the derivative of x raised to the 4th power. Alright, so then you go, oh, I know what to do. I use the power rule. Let me bring down the hammer. Bam! This guy knocks the 4 down. So the derivative of this guy is equal to 4. And then x raised to the, then this guy loses 1, 4x to the 3rd. And so that's the derivative of that guy. Easy, huh? Alright, let's do another one. Let's say, for example, you want to find the derivative of square root of x. You go, well, wait, you can't do the power rule, the hammer rule for that. Aha, but you remember this guy, square root, well, you can write that as a fractional exponent. This is equal to the derivative of x raised to the 1/2. So then you go, oh, bring down the hammer. Bring down the hammer. So this guy comes down. This is equal to 1/2 x to the, now if you subtract 1 from 1/2, you get x to the negative 1/2. Negative 1/2, which is simply equal to 1/2 times x to the positive 1/2, because you move it down, you know, to make it positive, which is then equal to 1/2 square root of x. And that's it. Now this is a good one to memorize, that the derivative of square root of x is 1/2 root x. So it's good to be able to go straight from here to here, because this one pops up so often.